Good morning, everybody. My name is Jack Lazarchuk, and I'm a developer at Chariot Solutions. Have you ever looked at the specific percentages and numbers in a service level agreement and wondered to yourself, how in the world is that calculated? In technology, we see them all the time, and I'm willing to bet a lot of people, myself included, don't know about the mathematics behind it all. That's why I'm very excited to announce Theo Schlossnagle, to introduce Theo Schlossnagle, founder and CTO of Circonus, who's here to talk to us about the right way to do latency service level objectives. Before I hand things off to Theo, I'd just like to say how appreciative we are that everyone has been so flexible with the conference changes, both speakers and attendees. So a big thanks to Theo and a big thanks to all of you. I will now hand this over to Theo.
Awesome. Well, hello, everybody. I am waving at you from Maryland in the Baltimore-Washington corridor, where I have been quarantined. So I hope you are enjoying wherever you are quarantined. So yeah, this talk is about latency SLOs done right. I will talk about the math behind latency SLOs, but I do think it's important to remember that most of the time when you look at an SLI or an SLO output, the math is almost always done wrong. So it's kind of a tragedy in our ecosystem that the vast majority of calculations around these things are actually done incorrectly by the tools. While I can, get on my soapbox and scream about why that's a bad idea, I will try to subtly leave you with the impression that that's a tragic mistake. Like a lot of things, if you do your math wrong, you get the wrong answer. So there are consequences to that. As Jack said, I'm Theo Schlossnagle. I founded Circonus in 2010, I think. And we focus on taking in high volumes of machine data and applying intelligence to that. So we have a machine data intelligence platform. We take in large volumes of data. We try to build behavioral models around that data and help people understand those models and kind of build like cohesive operational strategies around that data. In order to do that, you need to be able to do math on it. You need to be able to reason about what that math means, why you might do that math. It's kind of like anybody who's taken a statistics course. If you understand like how to take a mean, you're like, oh, I know statistics. Well, it turns out there's like 3 or 4 different types of means, and which one you use depends on the answer, the question you're trying to answer about the data set that you have. Knowing statistics, it's funny, I took statistics in high school, and then I took some graduate level statistics courses at university. And like, it's that whole, Dunning-Kruger effect, right? So by the time I finished my graduate level courses, I knew exactly that I knew plenty of statistics to do them, but not enough to know why and when to do them. So you hire a mathematician and move on with life. So I'm here to talk to you about latency based service level indicators and service level objectives. Because they're pretty easy to understand. Most of us that run online services, we run those services to provide various utility to users, whether it's buying product, interacting with other people, editing videos, whatever it is that you're doing with your users. You're providing a service that should be a pleasant and wonderful experience that keeps them coming back. One of the things that will always have your users looking for a competitive service is doing things slowly. So a long time ago at the O'Reilly conferences, the Velocity conference, the term "slow is the new down" was coined. But that's a long time since passed. I think everyone has kind of internalized that very seriously. So typically when we frame latency SLIs, which are service level indicators, we frame that as in the number of requests or the proportion of requests that we've served that are faster than a certain threshold. So if you look at that, there's some obvious questions: is which requests do I count? Over what periods of times do I count them? What is that magical threshold that's too slow? So I'll give you an example of one, which is, quickly to talk about an SLI and an SLO, there are competing definitions of what these things mean, but generally they're in the same vein. So a service level indicator is basically a measurement of something, right? It's a specific measurement of a facet of a behavior of a product that you think is important. And then you take those indicators and you look at them over a range of time with certain thresholds involved, and then that becomes an objective. So a latency indicator may be that, you know, I want to build an indicator around the homepage requests. Typically in most programming situations for like online services, it would be things like an API services that drives off on your mobile app, or search response queries if you have some sort of e-commerce solution, or maybe latency of message delivery if you're Slack, right? So like you have things around availability, you have things about being able to log in, but when I type a message and hit enter, how long does it take to actually show up on everybody else's screens, right? So like that sort of latency directly impacts my experience as a user. So that's the type of thing that you would, as a company, want to set an objective around. So we're going to get into how those indicators are measured and how to set those objectives. So a typical latency SLO would be saying something that like 99% of the work that I do, whether it's an API that I'm serving or a homepage request or whatever it is, over the past 28 days or month or however long, should be served in less than 100 milliseconds. And that's an interesting objective. You may find that objectionable, which I welcome you to find it objectionable. But how do you go about calculating that sort of thing? So I'm sure a lot of people have seen these types of graphs where you could look at the average, which is what we always used to look at 10 years ago. You would, you know, see all the latencies and you would graph them and you would see this line and you would say, oh, my latencies are great. But what you were really looking at was a line graph of the average latencies. So if you look at this graph, I mean, this covers more than 2 months, right? So it's from basically the beginning of June to almost the end of July. Every pixel in here represents one value. So if I, you know, look at this 50th percentile thing at the left side of the system, that's probably around 130, 140. What does that mean? What does 140 on that graph mean? So on the 50th percentile, all it means is that half of the requests that I served are faster on the bottom side of that, and the other half of the requests are slower than that. How slow? Well, that's a great question. So given the laws of physics, I can tell you how fast they could be. They can't be faster than 0. So we can't break the laws of physics and serve a request before it was asked for. So we do have a good lower bound on our latencies. 0 is a pretty solid lower bound. But an upper bound, we don't really have a good consistent upper bound. 1,000 milliseconds may seem like a lot, but I mean, it's only a second. I'm sure we've all written a service that had some sort of pathological performance case or a broken service in the back that caused a 15-second latency or a 30-second latency in that service request, which leads us to techniques in software engineering to help mitigate those, like circuit breakers. So you say 30 seconds, nothing should ever take 30 seconds. I would rather return an error in, say, 2 seconds or 5 seconds. And then you adopt circuit breakers and you'll see that you have somewhat of a decent upper bound of around the time of your circuit breaker. But you'll find in complex distributed systems, even with circuit breakers, you will have some interesting pathological cases where your 100th percentile, your maximum latency you ever see, is actually really a lot larger than you anticipated. You can see things that are in the minute to 2 minute to 3 minute range, right? So, and it all depends on how you measure those things. So we went over what 50th percent is, right? 50th percent is arguably a type of average, right? It's half things are bigger, half things are smaller. So it's typically in statistics called a median. It's not something we look at very often in computing, but statisticians look at it all the time. So you might want to ask yourself, why don't we look at it in computing that much? And the answer is because none of us are statisticians and we don't really know what we're doing. So 50th percentile is really useful. Typically what we see people do is try to eliminate, they want the service to work really well for almost everybody, right? So how do you define almost everybody? Well, I can tell you 50% of the people coming, not almost everybody. maybe 99% of the people coming to your, using your service is almost everybody. Maybe 99.5, maybe 99.9 is that big chunk that you want to optimize for. So what you end up doing is you start calculating, instead of an average or a 50th percentile, you start calculating a 99th percentile. And all that means is that if you look at this purple line at the top, the 99th percentile at each of these points means that however many requests were served where that pixel is drawn, could be 100 requests, could be 100,000 requests that were served there, 99% of those requests were faster. They were below the purple line. And 1% of them were above the purple line. Now, it's important to note that you don't know how much faster they are, and you don't know how much slower they are. So there could be absolutely none that are on that purple line. So a lot of this can be highly misleading to just look at the percentiles. But this is the typical view of that. So now we're going to get into sort of a problem of how this is calculated. So one of the problems here is that each of these pixels on the screen as you go forward in time represents all of the requests that happen in that little time slot. So if we're looking at like a 2-month view here, and you figure there may be like 1,000 pixels on the screen, say there's like 1,400 pixels on the screen. Well, there happens to be 1,400 minutes in a day. So, and there are about 60 days in the graph. So there's probably about 60 minutes in each of these pixels. So each of these pixels on the screen that are bouncing up and down represent all of the requests that happen in an entire hour. So if you can imagine at this little peak right here, on the right side, you have that peak at the top, we had a spike in our 99th percentile. How many requests actually happened in that hour or two that spike represents? This graph doesn't tell you that at all. So that's kind of an interesting caveat to this. So the problem is that if you're using tools like StatsD or a lot of the other variants that are out there, there's some internal tools like the metrics framework for Java and things like that. They use a technique for sampling the data that comes in to calculate a 99th percentile. And while that 99th percentile or 50th or 95th or whatever that they're calculating, while that has some good statistical properties around how it's collected, they're collecting it over a certain period of time, say every minute, every 5 minutes, right? So if I have in my system a 99th percentile measurement every 5 minutes throughout the month, and I zoom out and want to look at an hour, there is no way for me to calculate the 95th percentile over that hour. So if I have, say 1 minute samples, makes the math easier. If I have 61 minute samples over 61 minute 99th percentile calculations over an hour, and I want to know what the 99th percentile is over the whole hour, the answer is, I don't know. So this graph is showing me a number. That should be jarring right there because that number's wrong. It can't be right. There's no possible way to calculate it. What it did instead is what most line graphs do. As you zoom out and no longer have enough pixels, it takes the points that would comprise that pixel, just averages them together. So what you're actually seeing here is an hourly average of 99th percentiles, which statistically means almost nothing. So that's problematic. What it actually looks like when you go do the math is much wilder. So this is what, happens to be a P90, not a 99. But this is an accurately collected P90 over rolling 1 minute, right? So these are 1 minute P90s. And you can see it bounces around quite a bit. So let's talk about how we go about calculating these things, because I think a little intro to statistics might be useful. So typically, the easiest way to do this is that you have a log that has the latency of all the things that you care about. So this is like the classic way. If you're serving them out of a web server, or you're serving them out of an app, it writes a log that says, hey, I just served this API endpoint, or I just served this web page, and it took me 38.7 milliseconds, right? You write these logs out, and then you take the logs and you analyze them. And it turns out that you can do this with Splunk, you can do it with awk and grep, you can do it with elk. It's pretty easy. And it's also pretty easy to get the right answers, which is really interesting as well. The problem is that as your services get large and you do a lot of requests, it gets pretty untenable to answer the questions. It's hard to do the math in real time because there's so much data. And it also is not always easy to store it all, right? So if I want to calculate the 99th percentile and then I decide later, for example, that, you know what, 99th percentile wasn't the right thing. I really want to do 95th percentile or 99.5 percentile. I have to go redo the math, right? So I have to go look at last year's logs and last month's logs and last hour's logs. I have to look at all of those logs to recalculate everything. And those logs can be expensive, not only to do math on, but to store in the first place. So a great example of how to do this with something like Splunk is you take your data set and you say, give me the perc 90 as response 90 and perc 99 as response 99, and group it by application name. And what that will effectively do is give you a 99th percentile over that data. It's super, super simple. The way that 99th percentile is calculated, if you want to think about it as a computer science problem, is that let's say I have 100,000 requests that came in and I have their latency measurements. All I have to do is sort that list of latency measurements from smallest to biggest. And then I seek in that array 99% of the way through, and whatever is at that 99th percent is my 99th percentile. If I seek halfway through, I've guaranteed, because I've sorted it, half or less and half or bigger. If I go to the first one in there, I get my 0th percentile, which is my minimum. If I go to the last one, I get my 100th percentile. So once you've sorted those things over the time period you're looking at, a percentile is literally the percent through the array that you've sorted effectively. So pretty simple math. So another type of indicator that we should talk about, we won't dive into it too much, is not just things that are too slow. It's also errors, right? So errors, typically when you have an objective, you end up having several objectives. One objective may be, hey, I don't want any requests, or I don't want, more than 1% of my requests to be slower than 100 milliseconds. The other is, I don't want more than 0.001% of my requests to serve anything but a 200, right? I don't want any 500 internal server errors or other breakages, right? So there's a difference between slow, which you're trying to optimize for in one objective, and broken, which you're trying to optimize for in another objective. And we'll get to how you use these SLOs and why the math is so important in a little bit. So we talked about the logs. You can use logs. All you have to do is say, give me all the logs between, if you're doing a 28-day SLO, you say, give me all the logs for the last 28 days, sort all of the latencies, give me the 99th percentile of that. Super simple. Turns out if you have a high performance web application or mobile service and you're doing 100,000 requests a second, turns out 28 days worth of 100,000 requests a second is pretty brutal. It's a kind of a hard problem to interactively experience. You can't say, give me the 99th percentile. Oh, I mean 99.5. Oh, don't look at it at 100 milliseconds. Look at it at 250 milliseconds. Like, you can't interactively look at those questions because you have to really crunch and do a lot of work to answer them. So there is a different way to do these that's much more efficient, but we'll get to limited. This is just simply counting them, right? So as the requests come in, every time I serve a request that's, in our original example, sorry for the inconsistent examples, I talked about 100 milliseconds. This one is talking about 30 milliseconds, but you sort of get the point. What we're doing is we're counting all of the requests that come in, and we're also counting all of the requests that violated our threshold, in this case, 30 milliseconds. So now I have two numbers. I have a total number of requests, and I have a total number of bad requests. And as you can imagine, when you divide one by the other, you get the percentage of bad requests. So you know exactly what percentage you have at that you are serving well, right? So in this case, we're floating up. We can see the gray bar goes up and up and up, and then it goes up and up and up. And we have this red underneath it, which is all of our, I would say, unsatisfying requests, right? These are the requests that really didn't meet the objectives that we had set. So there's something really important to recognize about this graph. We'll get to it in a second. But as you are calculating this, because you're counting these things, if you want to know the percentile that is bad, effectively, all you need to do is take 2 points in time, say it was 4 p.m. to 4:30 p.m., and you subtract. So you say, I have had, this is like, well, like 60,000 requests at 4:30, and I had maybe 38,000 at 4, and I find the difference there. So now I know how many total requests elapsed in that time. That's a discrete derivative, a rise over run. And then I do the same thing for the red line. So it's a little hard to read here. You would use a legend in this case, but it's probably around 2,100 at 4:30 and probably around 1,700 at 4. And I take the difference there. So now I have the total number of requests that elapsed over that time. I have the total number of bad requests that elapsed over that time. And I can calculate an exact percentage of what we'll call a percentage of disappointment, right? A percentage of unsatisfied web requests or users. So this is fantastic. These are just 2 line graphs. That's all you have. You don't have tons of logs or anything like that. And the beauty is that you can, for any arbitrary period of time, calculate your percentile. I can do it for this entire time span from 6 p.m. all the way back to 0, I guess that looks like a.m., 6 a.m. back to midnight, or I could do it for a 10-minute period or a 1-minute period in there, as long as I have the numbers. Super simple. The thing that's really interesting about this graph is that there are some really long flat lines in this graph, right? If you look from like 120 all the way up to about 340, that's a relatively flat line. What does that mean? That means the total number of requests that I am getting is not really increasing there. So if I was to derive this, we would see a big hump from like 45 after midnight to about 120, and we'd see another big hump at like 340 to 430. That's when our traffic came in. We actually didn't have much traffic in the other times. So this brings us back to a question of, what do we care if the 99th percentile is bad if we've had relatively no traffic in that time period? Right? So violating your SLA when you're doing a lot of requests is much worse than violating your SLA or SLO when you're not doing a lot of requests, right? It's like, imagine being on stage and performing. You don't want to disappoint people. Are you measuring how good the performance is all by itself? Or are you measuring how good the performance is in context with the audience size? So if I have a really bad performance for 4 people, is that worse than having a mediocre performance for 50,000 people? The answer is no, right? I've disappointed more people in bulk because of the requests that were happening during that time, right? The audience size. So most SLO definitions do not adequately take into account that our services aren't uniform in their volume of delivery, right? The velocity of delivery. So if we were always doing 100 requests per second, then we could kind of just look at this naively and just say, an SLO is an SLO. But most of our traffic patterns don't look like that. If you're running a Grubhub, right, you don't have too much traffic at 4 a.m. No one's delivering that, right? You end up having these really interesting spikes around your time zones where people eat. Same with Uber, same with basically any service. I don't know of any service out there that has a very, very uniform request per second volume across days and weeks. So it's something to take into account. So how do you count these things? Just like I said, take the total number, you take the broken ones minus the total number, and you do your math, you get your percentiles. So what are the problems with this? So like I said, it's really cheap. You just count 2 things. This is great. But the problem with this is that we've counted things in our original example that are slower than 100 milliseconds. Now, when I invited you to take offense or take issue with the fact that I said 99% at 100 milliseconds, is because I made those 2 numbers up, 99%, 100 milliseconds. I'm like, why is that right? Maybe it should be 150 milliseconds. Maybe it should be 200 milliseconds. If I've counted things that are greater than 100, and then I decide, you know what, I should really have done 200, I don't have that data anymore. Like, I just don't know the answer at all. The things that I counted that were over 100 milliseconds, how many of those were there over 200 milliseconds? Well, I have no idea. So there is no way to go back and revise and iterate on your SLOs. And that is an incredibly important thing that you have to do, because all of these numbers are effectively pulled out of your ass. Like, you just have no idea what you're doing, and you kind of swag them. You say, well, you know, I read the Google SRE book and the example was 99% at 200 milliseconds, so I'm going to do that. Well, you know, great. That's not actually even accurate within all of Google, right? I mean, every different service has a different objective that they set relative to the consumers that are consuming those services, right? If I have a logging service, you know, the latency requirements for that may be really high comparatively. Like, I just need the things to get in within a minute, right? And if I have an authentication service or search service, I need things to come back and say maybe 50 or 100 milliseconds. If I have a disk block service where I need to be able to read and write disk blocks, those may need to come back in like 2 milliseconds or less, right? So like, all of those things are highly dependent on the type of service you're building. And, you know, I will tell you one thing I can guarantee you: when you choose that number the first time, it will not be the optimal number. So you need to accommodate that fact. So I will now talk about the right way to do all of this stuff. The right way to do this is to actually store statistical representations of the data that you can use to calculate these percentiles and thresholds arbitrarily, that are both inexpensive and fast. The beauty of using histogram data is that histograms can be aggregated over time. They can be used to derive arbitrary percentiles and inverse percentiles. And then the bin choices span the actual sample data, right? So if you all flash back to elementary school when you're talking about, or any sort of report you're reading on coronavirus, in fact, when you talk about who does this impact, and they look at different age groups, they say, oh, you know, this is the infection rate or the mortality rate or the recovery rate for people from 14 to 20, 20 to 28, 28 to 35, right? They have these bins and they're counting them. That allows someone to do statistics and reasoning about the behavior of something without looking at every single data point, right? These histograms are incredibly useful. There are four approaches. One of them doesn't really apply well, called higher order moments. It's a beautiful approach to histogram percentile calculations and things like that, but it's not commonly used in this situation. So there are three common approaches to this in our world, right? In the site reliability engineering world, the software engineering world, where we're looking at the latencies of and performance and behavior of systems. The first is HDR histograms, which is a high dynamic range histogram. And then there is a limited, very specifically built version of that called Circle-Hist, which is the Circonus one. These are all open source. And then there's T-Digest. So HDR histogram and Circle-Hist are both easy to reason about as non-statisticians. Basically, you have exact bins that exist in the system, and you put your data in the bins, and then you can look at it like a bar chart or whatever, and you can do your math on that. T-Digest is much more complicated. It uses basically kernel clustering around the probability distribution function of the data, and then it focuses on the long tail and ranges of change. So T-Digest ends up being incredibly accurate, but it does have an unquantifiable error introduction when you do merging of these two things. So if I have, say, a histogram that looks at last minute and a histogram that looks at this minute, and I want to put them together to look at both minutes together, T-Digest introduces an error that's harder to reason about than the zero introduced error from HDR histograms or Circle-Hist. So I definitely prefer the discrete histogram approaches that are in those. So this is what a histogram looks like. This is what a Circle-Hist looks like, which is a kind of a variant of this high dynamic range histogram. This is every single sample that has come in for a specific latency distribution. So this should look pretty common. I've got a big peak in the middle. The beauty is that I can calculate all of these vertical lines, this median, which is the 50th percentile, the average, the 90th, 95th, 99th. All of these things are calculated after the fact using the histogram. So I've taken all the data, I've created these bins. So basically the histogram is a set of bin boundaries and sample counts. So I can say, you know, in the what is this? Say like 370 to 380,000 bin, I've got 1 million samples. Once I have this histogram, I can calculate an arbitrary set of quantiles. 99th isn't what I want, 99.9, that's fine. 42, if you're into the Hitchhiker's Guide, right? 42nd, second percentile, you can totally calculate that. You can reason about the distribution of the curve. We can see here that there's one bump in the curve, right? This is what we call in statistics a mode. So if you look in like traditional, like elementary, middle, high school statistics, when you calculate a mode, it's the most commonly occurring number. So if we usually looked at data sets that were like 20 numbers long or 30 numbers long when we did statistics in primary education, mainly because it's a pain in the butt to work with bigger numbers. You sort of need a computer to do it. Well, it turns out when you have a big set of numbers, oftentimes you don't have a single number that is seen most often. You end up having distribution humps where we can say, hey, I've got a lot that are around 500,000 right here. I have a lot. It happens to be the median, doesn't need to be, right? But I've got a lot. There's a big hump there. But there are other curves that you can see, we'll get to those, that have multiple humps. And we'll talk about why that is and why understanding them is really important. And histograms give you insight into that. But the point is, this histogram is actually really inexpensive to store. This histogram ends up being somewhere between maybe 100 bytes and maybe 600 bytes. So for 600 bytes, I can store, this thing has probably like 6 million samples in it. I can store 6 million latencies and about 600 bytes. And after that, calculate accurate percentiles, inverse percentiles. It can tell you exactly what percentage of the population was below, say, 1 million, say 200,000. I can answer all of those questions with this. And it's a relatively cheap representation on disk, right? So it's cheap to store, it's cheap to recall, it's cheap to analyze. The beauty of using these histograms that look like this is that if I fix my bins, and I always have the same bin boundaries, I can take a histogram from last minute and this minute, and I can just add them together. All the bins align, so I can just add them up. I can take all the histograms from this hour and put them into an hour histogram. I can take all the hours from today and put them into today's histogram. And then I can take all of the hours and all the days and I can put them in months. And then when I want to ask a question of what was my 99th percentile for last month, it is literally a 1 millisecond or less operation to answer. I load a 600 byte or 1 kilobyte histogram that's been merged together, and I answer the question and I'm done. And I get super accurate answers. So it's great. This is what they sort of look like over time. If you imagine this graph where you've got the peak here, the peak would be the darker colors in the center, like the reds. And then the tails that have less would be these lighter, well, not lighter, but like the dark purple black colors. So if you imagine each one of these vertical bars is its own histogram, these are kind of turned into like a mountain range sort of view where you're looking straight down on it. I'm not going to spend much time on this. These are sometimes a little hard to understand. But the beauty of histogram data is that you can answer all sorts of really interesting questions, both inexpensively on the collection side, inexpensively on the storage side, inexpensively on the recall side and the mathematics side, and interactively quickly. And this is really beautiful. So one of the things that these that they answer, we've talked about percentiles, what's the 99th percentile and things like that. Well, it turns out that the percentile is not what people are usually fixated on. They don't say, what is my 99th percentile? They really say, I need my percentile to be faster than 100 milliseconds. So it's really important to understand that the 99th percentile is a latency. It's like 100 milliseconds or 180 milliseconds or 70 milliseconds. That is how fast 99% of your population experienced it faster than and 1% experienced it slower than. That is a latency. But the latency is a little bit easier to specify in a service level objective. When usually that's the one that is less flexible. You do your research and you say, you know what, if I deliver this service slower than say 250 milliseconds, I am disappointing users. So actually, I care what percentile that is, but I don't care what my 99th percentile is or my 99.5 percentile. I care what percentile is at 250 milliseconds or at, in this case, 100 milliseconds. And when I do the math on this is called an inverse percentile. So it's instead of f of x equals something, it's x equals f prime of something, right? So it's the inverse of this function. It's not how fast is the 90th percentile, it's what percentile is 100 milliseconds. And both of these things are easy to calculate via a histogram. And it's important to note when we looked at the counting method, which is, for example, the method that Prometheus uses. If you look at Prometheus, they say that they have histograms, but the way that you specify bin boundaries and the limited number that you can really spend, I mean, you can't. So for example, the circle hist has 43,000 bins in it, and that is enough. I'd love for it to have more, but it gets a little expensive there. If you tried to do 43,000 bins in Prometheus, it would not work at all. You usually end up getting around 8 or 10 bins. And with that number of bins, your error margin on calculations is astronomical. I mean, you can have things that are 1,000% off. So it's important that you set your bin boundary in Prometheus to the actual question you're answering. So if you want your things to be faster than 100 milliseconds, make sure one of your bin boundaries is on 100 milliseconds. And if it is on 100 milliseconds and you don't change 100 milliseconds, you can actually accurately answer the inverse percentile question of 100 milliseconds because it's counting everything and it's counting everything less than 100 milliseconds. You can choose, an arbitrary set of those bin boundaries, and then you can kind of get a little bit more robust. But it's important to remember that inside of any of those bin boundaries, because they end up being so wide, you have pretty phenomenally bad error in there. Also, remember that if you do not set all of your bin boundaries for all of your services the same, there's no way to add those histograms together. You just can't do it. They don't line up, so there's no good way to add them. So this is what an actual production histogram might look like. So if I showed you the median, the 99th percentile, the 90th percentile, the average, I guarantee you that you would not be able to tell me that this has two modes. Those statistical facets of the data aren't sufficient to see the modes. If I gave you the 5th percentile, 10th percentile, 15th percentile, 20th, like every 5, you could probably see it, right? That would probably work. But with a histogram, you can see there are two modes of operations. If this is a latency curve, I have a huge population of requests or services that are being served quickly in this first big hump. And I have a second set that are in this longer hump. Both of these end up looking like gamma curves in statistics. So the CDF or PDF functions tend to resemble composed gamma curves. So I have one gamma curve that's really high in the beginning. I have another one that's a little bit more latent, and they're kind of added together. So this, for example, would represent, this happens to be a CDN. So this is people on broadband versus people on higher latency connections like cell phones. So you can see you have a huge spike where people are getting very low latency service, and you have another longer population that's getting lower latency service. And it happens, it's very consistent because it happens that you have two populations of users that kind of fit in two buckets. But you will see this across all of your services when you do this. And it's really, really interesting information, because if you're doing an authentication service, for example, and you just need to check someone's credentials, I guarantee you will have two modes. You'll have one where it's in cache, and you'll have one where it's not. Not only that, if you don't even have a cache and you're using a database behind it, the database has a cache. You will see things that are hot in the database cache versus things that are not. And as you start to compose your systems together, you're going to see an emergence of 1, 2, 3, 4, 5, 6, 7 modes of operation. So why is that really useful? As you deploy new services, you can watch for new modes. So these are all modes of the distribution. So if is having 2 modes bad, well, I would say I'm not here to judge good or bad. I'm here to judge behavior. This has 2 modes. If I launch new services and turn something up and suddenly I have 3 modes, that is really interesting information. That's something to reason about. Why do I have that 3rd mode? What does that 3rd mode represent? Is it right? Is it a regression? Those are great questions that lead to really kind of profitable answers for a software engineering organization. This is what sort of a more realistic histogram sort of looks like. This is for 3 different types of service latencies for disks, right? You see microseconds of service level here. So I've got 3 different curves. I've got my light purple, my blue, and my yellow. They have resembled modes, right? So I have significantly more transactions that are happening in the light purple one. And the peak is a little bit later, right? So that ends up being around 4 microseconds, whereas the peak in the blue one, which has a little bit less, is lower. So those tend to be things like caches. So like the blue one is my normal sort of fast cache. My purple, the bigger one, is my fallback cache, where it's cached in the database. And then in this case, it actually happens to be like a NUMA miss or something like that, where I go fall back to my 3rd mode, which is the yellow one. So this gives you a lot of insight into the behavior of the system. And looking at this graph, it can be easy to remember, to forget that this is, 10 million samples that we're looking at. And all of this information is condensed in probably a few kilobytes of data to reason about. And I store that few kilobytes every minute or every 5 minutes, or if I'm really interested, every second. And I can look at how the behavior of my system changes over time. This data can help you inform how you set your SLO thresholds. This can tell you, is 100 milliseconds fast enough? Right? Once you have this data, you can start looking at the consumers of your service and say, hey, folks, when did you have a problem? And you could say, look, I had this huge problem where I was serving my stuff and it was all like 300 milliseconds long, and I have a SLI of 100 milliseconds, right? My objective around this is 28 days, 99%, less than 100 milliseconds. And for this entire day, was all up in the 300 millisecond range. You go to your downstream consumers of your service, and they go, I didn't notice. Everything was fine. Like, that is an indication that you are overachieving. Like, you should not be overachieving with service level objective. All right, so framing them, I think a lot of people talk about percentiles when most of the time when we're in the SLI, SLO world, we're talking about inverse percentiles. We're going over that a little bit. It's also really important to do the math right. And the reason that we have to do this math right is because when you set an SLO, you're making a promise to the rest of the organization, and typically there are hiring decisions and resource capital and operational expense decisions built around that. If I need to serve 99% of my stuff faster than 100 milliseconds and I'm not doing it, I need to invest. I need to achieve that objective, right? So the really important things to remember around SLOs are, first off, they should be the lowest possible objective you could set. Always the lowest. It's not like, I think I could do it 100% of the time faster than 1 second. I don't care what you think you could do. What do you need to do before downstream services are degraded? Right? This is the minimum possible level of effort to get a passing grade. right? And when I say a passing grade, this is the objective people expect from you so that they think you're doing an okay job, which think about it as like a 90%, like on a test. If you get an A, you get an A, right? You don't need to get a 99, you need to get a 90, right? Because the reason it's so important to set the boundary at 90, like an A, not an A plus, is because downstream services are not degraded whether you get a 90 or a 99. And if you set your objective to 99, someone's going to hold you accountable of hitting 99, and it turns out it doesn't matter. You could hit 98 and no one cares. Now, if you hit an 89, people start to notice, problems happen. And when people start to notice and problems happen, it means you should have invested. You should have managed to that boundary, right? So it's super important to set these things at the minimum viable objective. And this allows you to budget around it. So as you create these budgets, you can say, I need to deliver an A on this, not an A plus, an A. And you track through your month that you're trying to deliver on. So you have a 28-day delivery schedule. As you look at the trailing 28 days, you say, how close am I to this 90? If I'm at 99%, that means I can take more risk. I can do more code deployments. I can do a little less testing. Everybody likes to test in prod, right? You know, no one likes to hear that they like to test in prod, but everybody likes to test in prod, right? So the question is how much do you need to be careful about the quality of the code regressions, roll forward deployments, roll back deployments, all of that stuff. Well, if you have a ton of budget before you fail your SLO, you can take higher risks. You can move quicker. You can be cheaper. As you start to approach that boundary where you're like, you know what, we're at like 91% here. And if we drop below 90, we miss our objective. That's when you start screwing down the, twisting the screws. You say, we need to be more careful. We need to make sure that the service stability is more important than service progress and innovation, right? And these things are incredibly powerful. There's some really big companies out there that are using this to quantitatively allow their developers to kind of dial in how aggressive around innovation and release they are versus how they are around stability. And it's really nice to not have those things be super subjective. The important part of that, in order to achieve those, you have to be able to set your SLOs correctly. It has to be iterative. Why is 99.5 on 100 milliseconds right and not 99.2 on 115? And the answer is it's not, right? There's no way you're going to guess those numbers correctly. What you end up having to do is taking the golden signals, like the key performance indicators from your downstream consumers. And if you're on the front lines, that's your users. That's user attrition, user signups, all that kind of stuff. If you're in the back service, if you're a disk vendor, right? If you're providing like an ELB, not an ELB, elastic storage, right? Block storage, EBS, to consumers in your group, your downstream consumers are things like databases and stuff like that, right? So you need to understand what their objectives are and understand when they are in pain, right? And you have to be able to look at all of that data together and quantitatively circle in on a good number. 100 milliseconds is never going to be right? It's just ridiculous to think that you can arbitrarily choose a number and have it be the right one. So what you need to do is look at the last 2 months or 3 months worth of data and say, what would a better number be? What would 99.5 look like? What's 99.9? What's 75? What are the right numbers here where when I go below this threshold, I actually see negative impact downstream? Because that's that magical point you want to hit. And your software and your consumers are always changing. So you need to redo that. When you finally get those numbers right, congratulations, they will be wrong in a month. You need to redo that work. So you need a data science platform. You need an intelligence platform that can take this data and really turn it into something that sets reasonable SLO boundaries, right? Because if you're not using reasonable SLO boundaries, you are going to set these objectives and I have seen this in more than 50% of the companies that I've worked with that have matured their model, unfortunately not very well. People's bonuses are tied to these, right? You have a group of people that don't get their bonus when they don't hit the number, and you chose it arbitrarily. Like, this makes no sense at all, right? It's kind of batshit crazy. We have people that deploy 10 times as much hardware in Amazon to achieve an objective that was entirely unnecessary because they didn't iteratively go back and do the math to make sure that these boundaries were set reasonably. So the biggest takeaway is to make sure that you respect the accuracy, the mathematics around how you do these calculations, because they actually do almost directly feed back into budgets. So if you can imagine going into an accounting office and they say, well, can you give me the tally of, your spend for the month? And you gave them a number. They're like, how'd you calculate this? They're like, yeah, it's probably right. It's mostly right, maybe. It's an average of something. They would kick you out. Like, that's absolutely ridiculous. When you reconcile banks, they're reconciled to the penny for a reason. There's no reason that we shouldn't be doing that in computing. We're better than that. So that is, I want to stop really quick and see if there are any questions around that before I go into kind of the last parameter that makes this a little harder. How do you try to determine how frequently to iterate through SLO definitions is a question. So typically there are a set of quantums. So there's a quantum over which you measure your SLI. Like, what's my 99th percentile, right? So a lot of times that's done over, say, 5-minute or 30-minute boundaries. Then there's the time quantum that you use to actually manage your objective, right? Like, and that ends up being over a human reasonable time frame. It ends up being usually a month. Sometimes it's a quarter, but most people we see it's a month. I think really aggressive people go to a week, but going below there doesn't make sense. So the idea that I have this 28-day period when I'm trying to optimize for budgeting purposes, so month to month. So the lower end of how frequently to do it is that window, that human objective window for your SLO, 28 days. If you're doing a rolling 28-day thing, it doesn't really make sense to revise that and iterate faster than once every 28 days. What we typically see is people will do monthly objectives, and they'll do quarterly reviews. So every quarter they come out and do a kind of a reassessment of what's being monitored, what the indicators are. Are they still right? Usually the indicators are right. And then what are the objectives? Are these rational? Are these reasonable? And are these the lowest possible thing I could do to be successful? Everybody wants a bigger budget, right? You get your bigger budget by setting your expectations as low as possible while still achieving the optimal outcome. So I kind of hinted at this other time quantum, this 1 minute, 5-minute thing. So it turns out that looking at every single request over 28 days is very difficult for people to reason about because you have these spikes in traffic. So what people tend to do is they tend to cut these up into reasonable size chunks. So they'll say, I want to look at my 99.5 percentile and I want to make sure it's under 100 milliseconds over a month. But what I'm going to do is I'm going to look at it in 5-minute chunks. I got 288 5-minute windows every day. I've got 28 days. So I got that many windows. And for each window, I'm going to just look at are 99.5% of my requests, faster than 100 milliseconds. And if they are, that 5-minute window is a winner. And if they aren't, that 5-minute window is a loser. And then at the end of the 28-day window, I don't look at all of my requests. I end up looking at those 5-minute windows and figuring out how many windows that I win in and how many windows that I lose in. This ends up being a little bit easier for people to reason about. But it also accommodates sites with lower traffic. So if you have a site that's doing 15 requests a second, you're probably okay doing whatever you want. But if you're doing one that has 1 request a second or 1 request every 4 or 5 seconds, it can be really difficult to set any sort of SLO that's in the 99% range because you just don't have enough data. So what you end up doing is you expand that. So you expand this to like 5-minute chunks or 10-minute chunks, and you look at those chunks as your units. So another question. So log aggregation analytics tools like I think Splunk Slack, or APMs like AppD, all largely fail to utilize the histogram approach you're championing for P9099 over different periods. Is there any improvement in these tools on the horizon, or is Circonus and some emulators the only game in town? I think that, I mean, everybody's got to converge on this eventually. I think that, you know, in Splunk's case, you've already paid them to store your data. You're probably asking other questions of that data anyway. So for them, I think it's not so much of a financial optimization to let you store less, which is what we're focused on. It's more of a, how can I answer this question faster for my user to make it more interactive? So I imagine that a lot of those tools will adopt either T-Digest, higher order moments, or HDR style histograms, just in order to accelerate the query responsiveness of their systems. But there are a variety. I mean, I'd like to say that Circonus is probably the first system that implemented this in the wild. We deployed ours in 2011. But I think a lot of the competitors out there have followed on and have histogram-oriented solutions. And I think that is it. I think I don't have tool choices. I don't have very many more slides here. Hey, all right, there we go. I didn't have very many more slides. So I really appreciate everybody hanging out and talking with me. This is the first group of people I've gotten to talk to in many weeks that isn't my family. This is exciting. So I will be around a bit on Slack. So if you have any other questions or kind of want to ask about approaches to solve various SLO, SRE problems, I'll be around. Be happy to answer your questions.